Okay, let's continue with uncertainty. And we'll start this video by discussing suitable and confusing applications of variables for the addressing of uncertainty. Okay, so using variables to address uncertainty is a skillful task. If you do it right, it's informative. If you do it wrong, it can be confusing. So a suitable case could be the Tissos indicatrix. I think you have seen this figure in your cartography class because it's very famous for this indicatrix, Tissos indicatrix. It's very famous for addressing the distortion of shape and also the distortion of size in different map projections on the right. You can see that along equator, we have several black circles, right? They are in the correct size, they are in the correct shape, they are the baseline of the projection. There is no distortion along the equator. And when you are moving away from equator, the same circles become larger and more distorted when you are leaving, when you're getting far away from the equator. So when you're away from equator, it means that for this specific projection, the uncertainty increases because the distortion of shape and size increases as the distance between a location and equator increases. Okay, so this is a good example to show uncertainty. Okay, and a saturation is particularly logical for depicting uncertainty. If the saturation is high, you can say the uncertainty is high. If the saturation is low, you can say that the uncertainty is low. Or you can use the opposite method, like here. Pure or more saturated hues, they are for certain, unsaturated for uncertain. But there is no, say, law or rules for this, right? Saturation is a spectrum. Less saturated or more saturated, you can use it as you want, but you need to make sure that the meaning for different saturations is clear in your map using text or using legends to 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 make it very clear. Okay, so confusing example using size to represent uncertainty in stream position like this. Okay, so now we have two maps with linear features. We can consider them as rivers. So what's your first impression about the meaning of the width of these linear features? I would say for most people, the width should be proportional to the volume of the river. Or if these are roads, the volume of traffic of these roads. That's natural, right? But it's a pretty bad idea if you use the width of each linear feature to represent uncertainty, because that will be against people's first impression and will be confusing. So do not do this. Do not use width to represent uncertainty, okay? Because it's against people's natural feeling, okay? And there are other variable can be used to clarify uncertainty effectively. For example, crispness. Crisp boundary means reliable data, fuzzy boundary, uncertain data. Resolution, higher or finer resolution means the data is certain. If the resolution is pretty low, the image is blurry, it means that the certainty is low. The data is not that reliable. Transparency, the ease with which a theme can be seen through a fog placed over that theme. Okay, usually easily seen through the fog, it means that the data is reliable. Not easily seen through the fog, then it means that the data is uncertain, the uncertainty is high. Some examples here. First one, this is a map of whom do you hang with. It's from a website called where'sgeorge.com. This website is pretty interesting. It uses a specific method to track the movement of $1 bill around the country. For more details, you can go to that website to say. So here, let's get back to this map. So we have a lot of small regions in the United States, and they have blue boundaries. Obviously, these small regions, they are not states, right? Because they are not following the political boundaries of states, right? So these boundaries, they define the movement of $1 bills. For example, at the northwest corner of United States, here is a region includes Seattle. It means that $1 bills within this region, they generally move within this region. And because the boundary here, we can say it's a relatively crispy boundary, blue boundary. It means that most $1 bills within this region, they move inside instead of moving out. Another region here has an even more crisp boundary here, right? It means that pretty certain, the website is pretty certain that $1 bills within this region, they stay inside instead of moving outside. So the crisp here is representing the certainty, or you can say uncertainty. Let's just say uncertain. To represent that the crisp boundary means that the uncertainty is pretty low, which means most $1 bills will not go across this boundary. But we still have some very blurry boundaries with very, they're very blurry, sorry, with less crisp, right? It's not that crisp. So it means that, okay, here is a boundary between two regions, but we're not sure about the movement of $1 bills between these two regions. The less crispy boundary means that, okay, it's possible that some $1 bills, they will go across this boundary, okay? Deep blue, or we can say deep blue equals to crisp, right? This is as far as the most money goes, high certainty, or low uncertainty, right? On the other hand, light blue, fuzzy or blurry boundaries, this is as far as limited amount of money goes, low certainty or high certainty, or high uncertainty, right? Here is another example using resolution to address uncertainty. Here is a radar map showing the precipitation near Oklahoma City. So red areas and yellow areas, they are, this map is trying to tell you that within those areas covered by yellow and red, they are having pretty high precipitation. And green areas, they have relatively low precipitation. And you can see the spatial resolution here for this radar map is pretty high, because you can say the details of boundaries between red areas and green areas. So the spatial resolution here is pretty high. So let's compare with another one, this one. So you can say the spatial distribution of precipitation looks the same as the one I showed you in the last slide, but here less details on boundaries, on the shape of blue air of green areas and yellow areas can be provided by this map, which means that the uncertainty of this map is pretty high, and the uncertainty in this map is pretty low. Okay, which means this map is reliable, this map is less reliable. What's the difference? This map with high spatial resolution and low uncertainty is made by what? By archived data. It's the history, it's the past. Of course, it has happened, so it's accurate. We observe that. this is for future, this is for prediction, right? So if you compare this with the archive data, of course, the certainty of this map is low, uncertainty is high because it's prediction, it makes sense, right? Okay, here, transparency, how to use it for uncertainty. Here is a map, a contour line map. I think it's the variable transparency is used to depict the uncertainty of the data, right? It could be air pressure or other variable, but it doesn't matter. A light fog indicates reliable data, whereas a dark fog in the center of these two areas indicates uncertainty data. So here, less transparent part is for high uncertainty. Transparent part, more transparent part is for low uncertainty, right? And you can use it the other way. For example, here we have two, say two fogs. A big fog covers a larger area. A smaller fog covers what? A smaller area. But what's the meaning of that? Both fogs, they are indicating areas affected by Katrina. And both of them, they are predictions. Okay, so why the one predicted in 2005 is larger than the one predicted in 2015? Because the model used for the forecast developed in this 10 years. So in 2005, according to the model, this huge large area would be affected by this Katrina storm, right? And it's less certain, which means that the light fog here is for area with higher uncertainty. And in 2015, due to the development of the model limited the area affected by Katrina to a smaller region, right? The region covered by the darker fog. So the area affected by Katrina predicted by the model decreased a lot according to this model. And this small area here is more certain than the large area to be affected by Katrina, okay? And this is transparency. And we can also use intrinsic variables to show uncertainty and also the variable in one map. In maps combined method, here are some examples. Okay, and also we can also use map combined extrinsic method to do this. For example, utilization of glyphs. Okay, so here we have two figures. So figure A and figure B. Figure A is a traditional approach for depicting wind speed and direction. So we have a lot of small arrows. Each arrow, of course, has a specific direction. That's for the direction of the wind. And each arrow has a length. The longer the arrow, the higher, of course, the speed, right? And also in figure B, each arrow has a weight right now. Okay, which means that another symbol has been introduced to address what? To address uncertainty. Okay, and the weight of each arrow is related to the uncertainty. Okay, the weight of the arrowhead indicates uncertainty in direction, and extra arrowheads indicate uncertainty in speed. Okay, and here is a 3D visualization for the same topic. And this example is also for maps combined method for uncertainty addressing. So here we have 4 maps. They were all produced by a remote sensing method called fuzzy classification. So in remote sensing, a very common application is find out the land cover type of each pixel within the area of interest. Okay, for example, a pixel A is soil, bare soil. Pixel B is water. Pixel C is vegetation. In traditional classification methods, a forest is a forest. It's a yes or no. But fuzzy classification is different. In fuzzy classification, each pixel here is given a specific, it's called membership value. The higher the membership value, the higher the probability that this pixel belongs to a specific land cover type. For example, if a pixel is given a membership value of 0.9, okay, it means that 0.9 for forest, it means that this pixel is very likely to be forest instead of giving a judgment of yes, it is a forest or no, it is not a pixel for forest. Okay, so this whole image here is giving you information about what? About uncertainty. If the membership value for a pixel is pretty high, it means that uncertainty is pretty low for a specific land cover type. For example, membership map for bare soil in the Upper Lake McDonald Basin Glacier National Park. That's the theme of figure A. So we have bright pixels and we have dark pixels. Bright pixels means that the membership value is pretty low for soil. Dark pixels means that, wait a minute, let me say this. Okay, that was my mistake. If a pixel has a very bright color, it means that the membership value for soil is pretty high for that pixel. If a pixel is pretty dark, like all those pixels in the center, it means that the membership value for them is pretty low. Okay, that membership value is for soil. What does it mean? If you're looking at figure A, it means that most of the area is not covered by bare soil. Okay, only a limited number of pixels here, 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 and right here to the south. They are bright pixels. Their membership values for soil is pretty high. It means that it's very likely that they are bare soil. Okay, so let's just check out say. Say is membership map for alpine meadows, vegetation. So it makes sense, right? So for those areas that bare soil cannot be found, they are covered by vegetation. Okay, so the output of fuzzy classification is actually images, right? And image, for each image, each pixel in that image is giving you uncertainty information through something called membership value. The higher the membership value for a specific land cover type, the lower the uncertainty for that land cover type. Okay, and we can also use dynamic representation to address uncertainty. Users need control over depictions of uncertainty. And there are two fundamental strategies for interactive visualization of uncertainty. Bivariate representations that depict data on uncertainty together. Users control which component is visually dominant. If you care about the data itself, you can make it more obvious. Or if that is not the case, you want to show uncertainty as a dominant element of your map, you can change it. You can interact with the map, or depict only data but allow users to control an uncertainty threshold above which the data are not represented, or are represented less clearly. It means that, okay, I will show data first in the map, but also uncertainty data has been added to this geovisualization, but it is not directly shown in the map. And your users can assign a specific threshold for uncertainty and say that, okay, if the value, the actual data within a specific area has an uncertainty higher than your threshold, then I cannot tolerate that. You should just hide them. I only want to say the areas with less uncertainty. Okay, that's called threshold method. Here is an example. So we have three figures here. The left one is case one. The right two figures, they are case two. In case one, bivariate representation that depicts data and uncertainty together. So this is a map showing the nitrogen concentration of a river. Okay, of a river. So the saturation here in this map is for what? Is for the concentration of nitrogen. And the different hues, they are for uncertainty. If a pixel is in blue, it means the uncertainty is pretty low, the data is reliable. If a pixel is in red, it means that the uncertainty is pretty high, the data there is unreliable. Okay, so this is using one map to show data and uncertainty simultaneously. Okay, so on the right side is the case for interactive mapping or interactive geovisualization to address uncertainty. It's the same thing. It's the same. It's the same topic. No matter on the left side or on the right side, the saturation here is for the concentration of nitrogen. But you may have noticed nothing here is used to show what? Uncertainty, okay? Because you need to assign a threshold. On the left side, we have the whole map, no matter the uncertainty. On the right side, the user assigned a specific threshold for uncertainty. If the uncertainty is higher than that threshold, that area, that pixel will be what? Temporarily hidden. That's the reason why you can say that not the whole watershed or this area was shown, only the central area of the watershed has been shown. Because if you compare this part with the blue part on the left side, this is a part with high certainty or low uncertainty, right? And the rest area, most of them, they have been hidden because they have high uncertainty and they are portrayed in red on the left, right? It makes sense. So static geovisualization, showing data and uncertainty in one map. Interactive geovisualization, showing data and uncertainty through what? Through interaction. You need to assign a threshold, okay? And using that threshold to decide which part of the map you want to know, you want to say, which part of the map you don't want to say, okay? And you can also use animation to show uncertainty. For example, here is a frame from an animation showing the pressure surface. The predicted pressure surface was represented by ISO lines, right? It means that along each ISO line, the pressure stays the same. Areas of disagreement between different prediction models were represented by colored areas with various saturation behind the data depiction. Okay, so more saturated areas are the areas for higher uncertainty. Less saturated areas, they are for areas with what? With lower uncertainty. Okay, this is a frame, a single frame of the animation. If you list multiple frames and put them together, order them by time and show them one by one quickly, you will have an animation. And for this specific frame, it's a prediction of pressure surface at a specific time. And at this specific time, different areas saturated, they are for disagreements for between models. And you can do this for multiple days or multiple months or even multiple years and order them, make an animation. You will say the change of what? Of the change of areas with uncertainty. Okay. And here is the last example, applications of varying uncertainty, and it's from a research. Okay. They're needed, more research, studies are needed to evaluate the effectiveness of uncertainty visualization tools. So the authors of this specific research, they use different methods to address uncertainty. Okay, let's say what they are. The first method, okay, total reports of disease D in Costa Rica. Here, gradual symbols, they are used to represent the number of cases, right? Circles with different sizes, they are used to portray different numbers of cases. And here in map A, a text is used to address uncertainty. Totals derived from data collected in and around San Jose, I think this is a city, right, are most certain. Data certainty decreases away from San Jose. Okay, so a text has been used to address uncertainty. Secondly, an indicator map is used to address uncertainty. In this indicator map, we have 3 areas with 3 saturations. The most saturated area, I think that's San Jose, right? San Jose is here. You can say it's most saturated, it's black. It's an area with what? Let's say total derived from data collected in and around San Jose are most certain. So the most saturated area is the area with the lowest uncertainty or highest certainty. And when we are moving away from San Jose area, what? The certainty level decreases. Okay, so that's the second method. Use another small indicator map. The third one, data certainty level is addressed by the crispness of what? Of the boundary of these gradual symbols. If the boundary of the circle is pretty crisp, has high level of crisp, is very clear, then the certainty is high. If the boundary of the circle is blurry, is fuzzy, then the certainty is what? Is low. Uncertainty is high. The last method here, use what? Use the saturation of each gradual symbol here to represent uncertainty. If it's fully saturated, the certainty level is high, the uncertainty is low. And if you compare 4 of them, it's subjective. Different people may have different ideas. My personal opinion, I think the last one is the best one. The size of each circle is for the actual number of cases, right? And the saturation of each circle is for uncertainty. If it is fully saturated, it means that the data is very reliable and the uncertainty is low. But according to the result of this research, focus, bottom left, outperformed what? Outperformed the value, bottom right. I'm a little confused about this result, but if that's the result from the research, that's it. But I want to say that you can say it's about map design. It's about people's perception. We have principles, but there is no so-called correct answers, right? If I was the one to produce this map, I would use this method. Okay. So what are those challenges when we're dealing with uncertainties in geovisualization? Firstly, understanding the components of uncertainty and their relationship to domains, users, and information needs, and also understand how knowledge of information uncertainty influences information analysis, decision making, and decision outcomes. You should be aware that uncertainty is always there and it has impact on your analysis and further decision making. Okay, you should not look away from it, try to avoid it, try to dodge it. It's not healthy. Okay. Okay, and understand how or whether uncertainty visualization helps exploratory analysis, and developing methods for capturing and encoding analysts or decision makers uncertainty. So developing representation methods for depicting multiple kinds of uncertainty. I have introduced some methods in this lecture about how to depict uncertainty in geovisualizations, but obviously there are more. And even with limited numbers, limited number of methods I've introduced here, sometimes it would be more difficult to choose from one of them to accurately and efficiently address uncertainty. So it's a very complex job. Okay, and developing methods and tools for interacting with uncertainty depictions. I would say if you are not an expert in geovisualization, developing interactive maps would be a bad idea because it's very tricky and more complex than static map making or geovisualization making. So be careful with using interactive mapping methods for uncertainty. Okay, and assessing the usability and utility of uncertainty capture, representation, and interaction methods and tools. Okay, it means that we have mentioned this before, right? In the first lecture, it's about usability. Usability. You nowadays, when you make a map, especially make a map or geovisualization for the public, you always want to collect. You always want to release an original version and collect ideas from people, comments from them, and iterate and your data, your geovisualization, and make updates, right? To make sure that they are becoming more and more useful. Okay. Okay, that's all I want to say about uncertainty in geovisualization. And thank you for watching.